Hello students, my name is Shashank Shekhar and today is the fourth lecture of the chapter Aldehyde Ketone and Carboxylic acid. So far we have seen some methods for the preparation of aldehyde and ketone, but those were some common methods. So if you look at the syllabus here, so we have covered this nomenclature part. We have seen the nature of carbonyl bond. Of course, we have not related with the reactivity of that carbonyl compound, but we will soon see it. Okay. Then we have started with these methods of preparations. Also, we have covered some common methods, as I have told you earlier, like our hydrolysis or say hydration of your alkynes, or I would say ozonolysis of alkenes, or oxidation of alcohol. So those were some common methods. Okay, but some specific reactions are also there which are specific to say aldehyde and ketone. Okay, so we'll see all of those today along with the mechanism. Some of the mechanism may look very complicated to you, but believe me, as you will see the reaction mechanism, the reaction would make somewhat sense to you. Just learning or you can say remembering the reaction is not so beneficial. If you look at those mechanistic part, then you will be able to appreciate the reaction. Clear? Okay. So let us start our today's class. So if you look at today's topic, so these are the name reaction that we will cover today: Rosenmund reaction, Stephen reaction, then the use of a specific reducing agent called as double H. Further, we'll move to Itard reaction, Guttam and Koch. Okay. Oh, sorry for this. Then we will see preparation of ketone. So these were all the methods of preparation for aldehyde. So this is for aldehyde. And this we will see 2 to 3 methods of ketone. Clear? So let us start our today's lecture. So first of all, we will just give a revision to the Rosenmund reaction that we have studied yesterday. So what was the Rosenmund reaction? Basically, we have a acyl chloride and we treated it with H2PdBaSO4. There are 3 components of it. H2 is the reagent, PD is the catalyst, BaSO4 is the poison. Poison means that controls the rate of reaction, or you can say deteriorates the rate of reaction, because applying PD would result in drastic reaction condition. So to control the activity of this PD, we take this BaSO4. Clear? So what was the mechanism? So if you remember, first of all, the palladium metal get inserted between the bond of carbon and chlorine. So in this step, we can see metal insertion is occurring. This is called metal insertion. So metal is being inserted or being involved between the carbon and chlorine bond. Further, our reagent is hydrogen. So this hydrogen, due to the high electronucleophilicity of this, the high nucleophilicity of this carbon, because of the presence of a very electropositive metal, that is palladium, this hydrogen will be able to do a nucleophilic attack on this center. So it will donate one hydride, and one hydride will be donated on this center, plus one H plus will be released because there are 2 electrons between hydrogens, one here and one here. So both of these electrons are taken up by this hydrogen, suppose. So it will take both of these electrons and it will attack here. And the remaining H plus will be summed up with your Cl minus, that will be released. Plus we will get our PD back. Clear? So in this way, the reaction is being progressed. You can see that we are left with this PD, which was the catalyst. Its concentration is not changing throughout the reaction mechanism, and the reagent was H2, whose say this concentration is changing, because this H2 is now converted to this aldehyde part and your Cl minus counter ion. Clear? So there is a nucleophilic attack of this hydride. So this was our Rosenmund reaction that we have studied yesterday. Moving to our today's reaction, the next reaction is Stephen reaction. So basically what do? We take a nitrile. So this is a nitrile. Nitriles look like this. So we have R, then C is triply bonded to the nitrogen. So if we treat our RCN with this, say our SnCl2 and HCl, so nitriles are reduced to imine with stannous chloride. So this is called as stannous chloride, that is tin, in the presence of hydrochloric acid, which on hydrolysis give our, say, this aldehyde. So what it is written? So we take our nitrile, clear, and we take this SnCl2 and we react it in presence of an acid. Then we get this imine. This is called as imine. I have put up the picture earlier also of amine. So basically what is done here, that this triple bond O has been reduced to C double bond O N. You can think it as a derivative of your, say, this aldehyde, where we have removed this O with N. Okay, not N, I would say NH, because N had a valency of 3. Yeah. Okay, so this thing is called as imine. It looks like this in a structural form. Clear? After the hydrolysis, so remember this thing, that imine is very say reactive towards water. It quickly deteriorates and form your RCHO bond, because you know that this carbon double bond nitrogen bond is not stronger as this C double bond O is stronger. Clear? The reason is very clear, because of the higher electronegativity of the oxygen. Now, if you look at the mechanism, it looks bit complicated in first sight, but believe me, it is very easy to follow. Just keep track of the arrow pushing mechanism. Clear? So we have, first of all, we have our RCN, that is nitrile. Now I have told you that HCl will act as a catalyst. So it will first protonate this. One, I would say, suggestion I would give you, that whenever you see that acid is acting as a catalyst, then most of the chances is there that it will just protonate the substrate. So it will protonate which of these? Now carbon cannot accept this hydrogen because it has no lone pair. Similarly, this alkyl group must be carbon. Now we are left with this nitrogen, which has a lone pair. So it will donate its electron to this H. And we will get this kind of adduct, where we have Cl minus and the counterpart is RCNH plus. Now we have our reagent, that is SnCl2. Now what is SnCl2 made up of? It is made up of one Sn and 2 Cl, and Sn, since it is a metal, so it is also containing electron. And you can see very clearly that, okay, this nitrogen is being positive, so this will create a greater delta positive charge on the carbon. Now you can also argue in this way, that why does not it has a positive charge, why does not this SnCl2 donates its electron to NH plus? Because it has no empty orbital to accept that electron. Clear? So if you think it in a way that this is increasing the nucleophilicity of these carbon. Okay, so it will donate one electron to this carbon. One electron will be donated. So sorry, there should be a fish hook arrow here rather than a double-headed arrow. There should be a fish hook arrow because one electron is donated. Okay, sorry. Okay, yeah, 2 electron is donated in this thing. Okay, so what happens? One electron is donated. One electron is donated, and we get a radical. So this double bond goes on this thing, and it creates a double bond. So it is shown here also. Yeah, it is shown here also that this is donating the pi electron. Now, since you have donated one electron on carbon, it will result in the formation of a carbene. So what is carbene? Not radical. And how much electron does radical have? 1, 2, 3, 4 and 5, 6, 7. 7 electrons. 1, 2, 3, 4, 5, 6, 7 electrons. Yeah. So it has 7 electrons. Now since it is unstable, so again what will happen? Since this SnCl2 has donated its electron to this carbon, it must have acquired a positive charge, but it is neutralized by the Cl minus, because as soon as this pi electron goes on nitrogen, this Cl minus has no counter ion to interact with. So it goes with this SnCl2 and form the SnCl3. Now again this SNS electrons left in this orbital, valence orbital. So it will again donate its electron and form the carboanion. Carboanion will be formed. Now this carboanion has a negative charge. As soon as the negative charge is formed, and since we are doing the reaction mixture in the mixture, and mixture also contain H plus, so this negative charge will take the H plus from here, and it will result in these kind of substrate. Okay, this is called as imine. This is called as imine. And again, since this H plus has been taken and Cl minus has been left out, so this again, this Cl minus will go to SnCl3 and form SnCl4. This is the mechanism. Now next, what will happen? Next, this HCl will again donate electron. Okay, HCl will again donate electron, and this time 2 moles of HCl will donate electron. So suppose this reaction is going on and we have formed 2 moles of the imine. So this reaction goes twice and forms 2 moles of this amine, and both of this amine molecule are being protonated by 2 moles of HCl. So it would form 2 moles, this one and this one. Plus, since SnCl4 is being involved in all of these, therefore SnCl6 will be formed, because this SnCl4 will again get 2 Cl minus from 2 HCl, and SnCl6 octahedral complex will be formed carrying 2 negative charge, and the counter ion that is present is this 2 protonated imines. Clear? Now we know that if we do the hydrolysis of this, we will get this thing hydrolyzed to SnCl4 and RNH3 plus. Clear? So what will happen here? So what is happening here is that, suppose there is a H2O molecule, it will attack on this side. This will move here, and further this H plus will be transferred from oxygen to nitrogen to form this kind of thing. Clear? Now we are left with this SnCl4, 2 Cl minus are kicked out. So one of the Cl minus will take the H plus and will result in this kind of aldehyde plus NH4Cl. So this is the overall reaction. So this mechanism looks complicated, but believe me, as you go through the mechanism twice or thrice, you will get a handle of it, that how to look upon the mechanism. Clear? So I would suggest you to start building concepts about knowing the mechanism of the reaction. Clear? So this was the Stephen reaction. Now next we will move to dibyl H. So this dibyl H is kind of a hydride donor. So this is our dibyl H, that is diisobutyl aluminum hydride, dibyl H. So it looks like this. So why is it named so? So it is first written as diisobutyl. So this group is called as, wait a minute, yeah. So this group here, this group is called as isobutyl, and since 2 are attached, 2 of such kind are attached to the aluminum, therefore 2 isobutyl, diisobutyl I would say, diisobutyl, then aluminum and hydride, one hydrogen is present, so hydride, that is short abbreviated as dibyl H. Okay, so this reagent is very you can say very handy. It would result in a transformation of various functional group to various required functional group. This depending upon the number of or the molarity of the dibyl H that has been used. Now suppose we are using ester and nitriles here, and we are reducing it in the presence of dibyl H. Now if you remember the previous class, we were using the, say, our preparation methods, we are looking upon the preparation method of alcohol. You must have seen that we have certain reagents like LiBH4, LiLH4, they all were hydride donor. Similarly, this is also a hydride donor, but a softer one. Okay, but a softer one. But it has one advantage due to this complex. It can coordinate with this, say, our nitrogen lone pair, or say our ester lone pair, and therefore it can attack more efficiently. Suppose we take the example of RCN, that is our nitrile. So if we treat it with our dibyl H, or you can say diisobutyl aluminum hydride, then it would result in the formation of RCHO, that is aldehyde. Or we can also use a say nitrile containing double bond. Still it will only target on the CN, and it will not look upon this double bond. So you should note this thing, that if we have a double bond and you are asked to reduce a nitrile to a CHO, then you will be using this dibyl H. Now how does this mechanism goes? Very simple. It has a hydrogen, a hydride. So it is hydride attacks this nucleophilic center, because this nitrogen is more electronegative. It has a delta negative, a delta positive charge. Now one more advantage, as I have told you, that this has a power of chelating. So this lithium plus ion chelate with the lone pair of the nitrogen. Okay, so since this chelate with this thing, it increases the nucleophilicity of this carbon group. or the carbon center. Therefore, this hydride is donated by the aluminum to this center, and it results in the, say, moving of this or propagation of this triple bond onto this nitrogen. Clear? And it forms a bond such like this. This is called imine salt. Okay, this is called imine salt. Further, as I have told you that as we say expose our imine to hydrolysis, it quickly goes to imine and further to your RCHO. So it is not mentioned here. So this will be further converted into RCHO. Okay. So remember this. I'm again suggesting you to remember this thing, that as we expose our imine to hydrolysis, it quickly gets converted into your aldehyde. Okay, clear? So this was your reaction of diol H with nitriles. Now we will see how it reacts with esters. So you can see that we have ester here. It reduces this ester to your ketone. So instead of writing that complete isobutyl, I have written just diol H, is short form. Do not get confused. Try to remember both of the names. Okay, this diisobutyl ammonium hydrate along with its abbreviation and structure also. Structure is very important. So this structure is very important to remember, because this is only trying to specify, or you can say it is evaluating this reaction. Clear? So how does the reaction goes? So we have an ester here. You must have remembered that we were using BF3 earlier, and BF3 was specific to your carboxylic acid, but it was not reducing this ketone or say aldehyde. The reason was that because its mechanism was opposite. Because first the electron is donated to this BF3, and then it it was BH3. Sorry, yeah. First the electron was donated to boron, and then hydride was donated to the say the group which is to be reduced. Now this is the same. Okay, this occurs in the same way. Since this this oxygen is donating its electron, increasing the electron density on this oxygen, so this oxygen will eventually donate its electron to this aluminum and form this kind of complex. Okay, you can see very clearly that this is being formed. Okay, now further what will happen? This hydrogen will be donated, or hydride, I would say hydride, not hydrogen. So this L is now containing a negative charge, so it will donate its electron to this thing, this center, and it will result in this kind of bonding. Okay, now further what we do, we quickly do the hydrolysis, or you can say addition of mild acid with warming. So this would result in breaking of this bond and would result in final aldehyde. Clear? So this is the mechanism of diol H, both with ester and nitrile. In the previous slide we have seen the use of nitrile, so I think that mechanism was wrongly written. So that would be written in this way. Okay, because we do not have any counter ion in case of this aluminum, and I am very sure about it. So it would have happened in this way only, similar to this mechanism. So we have a structure like this. We have a hydrogen. This lone pair would be have first been donated to this aluminum. Okay, and this kind of structure would have been formed along with the hydrogen and 2-diisobutyl. Okay, then further this hydride must have been donated here to form this thing, and as the imine is formed, this is quickly being hydrolyzed to your aldehyde. Okay, so this ketone, sorry, nitrile would have followed the same mechanism, similar to the ester one. This one is the correct one. Okay, because we do not have a counter ion in case of lithium, because diol H is a neutral species. Clear? So the next is Etard reaction. Now I would suggest you that you must not worry about the mechanism much, although I put it here. because just to you can say satisfy your curiosity, but you do not have to remember the mechanism, because this reaction is mechanism is very complicated and is way beyond your scope. Okay. So these are the two reactions that I've given. So the first, this is the Heat-Art reaction, and this is just a, you can say, different type of reaction that does not it is not in the say league of this Heat-Art reaction. Okay, I've just put up this here because it looks like similar. Okay, yeah. So we have chromyl chloride. This is called chromyl chloride, CrO2Cl2. So it oxidizes the methyl group, that is CH3, and further on a hydrolysis of this we get this benzaldehyde. Okay, now this reaction follows concerted mechanism. There is no formation of electrophile nucleophile, no charge species are formed, and for that to promote that, we are using CS2, which is a non-polar solvent. Because if there was a formation of, say, any intermediate which is positive or negative charge, then there must be a polar solvent that would stabilize the intermediate. But since this mechanism goes through a concerted mechanism, and I am saying that this is more efficient, the concerted mechanism are very much efficient than your normal reaction, because they go in one step. So the you can say your yield is very high. The amount of substance that is formed is very close to your expected product. Okay, because there is no loss during the formation of the intermediate, because intermediate can result in breaking back to your reactant part. But since it goes in one step, the concerted mechanism, the yield is very high for this kind of reaction. And plus, if you see such kind of solvent, then you can think of this reaction. Now let us see the mechanism. So as I have told, all of these steps occur in the same step. All of this thing, transferring of electron, acceptance of electron, all of this take place at the same time. So here we are with a methyl benzene. Okay, that is toluene. First, this pi bond is being donated to the chromium center, which has an empty d orbital. Now it is electron rich, so therefore it will donate its pi electron between chromium and oxygen to this hydrogen, and it will form this kind of intermediate. So this thing is now present as OH here. Okay, now something it is called as EN reaction. You do not have to worry about it. I'm just saying writing it for your curiosity. It named as EN reaction. Okay, now further it goes 2,3 sigma tropic. You do not have to worry about the name. So if you are interested in how it is named as 2,3 sigma tropic, basically it goes like this. So basically what we are doing, we are forming a bond between these things, here and here. So its arrow pushing is not done properly. Okay, so let me draw it for you. Yeah, we have our OH, we have our two Cls, we have our double bond O, plus there is an hydrogen, sorry, not a hydrogen, plus a double bond. Now what will happen? This thing will move here. Okay, this thing will move here, this bond will go here, and this will be going here. Okay, so this is the concerted mechanism. So if you draw the intermediate, or I would say transition state, that would be a more appropriate word. So transition state looks like this. So let me clarify with this thing. So these are not the complete bond, they are just the interactions. Yeah, then we have this thing which goes like this. So if you see all of the red lines, these lines are not representing the bond, they are representing the transition state, that the bond is not still formed or is not still broken. They are on the phase, or you can say virtue of being broken or being formed. These are not formed bond. Okay, so these are being say represented by dotted one rather than the simple dashed lines. Yeah. So this is the transition state. So look how beautifully this reaction goes. Okay. How beautifully this reaction goes to form this intermediate. So further, the bond that are to be broken and to be formed are being proceeded, and we get this kind of thing. So we have Cl minus in the reaction mixture. This will take the H plus and will kick out this thing to get our aldehyde. Okay, so this is a benzaldehyde formation using our toluene. So we take a chromyl chloride, and it results in the formation of chromium complex, which is being further hydrolyzed to your aldehyde. Okay, now this is another reaction which is different from this. So what we are doing, we are doing the side chain chlorination of this toluene. So first we have done the side chain chlorination, and further upon hydrolysis it gives you aldehyde at very high temperature. Okay, at very high temperature. Next we will move to Gautam and Koch reaction. So if you look at the reaction, how would this reaction mechanism would appear to you? Just think of it. Okay, I am just telling you to think of the reaction mechanism, because this reaction you have seen earlier, only the way of representing is very different, but it is a familiar reaction. So what happens in this reaction? So in this reaction we treat our benzene with this carbon monoxide in presence of HCl and anhydrous AlCl3. If you remember, you must have seen this AlCl3 somewhere. Okay, just try to remember it. Okay, if you got it, well, good. If not, it is Friedel-Crafts reaction reagent. It is a Friedel-Crafts reaction reagent, which it is used as Lewis acid, and this reaction is nothing but Friedel-Crafts variation. Now you would ask how. So if you see here, we have a CO. Okay, we have a CO, and plus we have a anhydrous AlCl3, which form this kind of adduct. Okay, this will carry a positive charge, will carry a negative charge. Now due to the formation of charge on oxygen, this will increase the nucleophilicity of this center, and this pi electrons will attack on this. Okay, this would result in moving a bond here. Clear? Now on further hydrolysis, we give a benzaldehyde. So what is this overall reaction? So in this overall reaction, this is the catalyst, that is a Friedel-Crafts alkylation or Friedel-Crafts reaction catalyst. This is your reagent that is being attacked by your benzene, and hydrolysis in presence of HCl of that complex that is formed gets our benzaldehyde. So it is nothing but your electrophilic aromatic substitution reaction. Okay, it is a electrophilic aromatic substitution reaction, but you can see that the reaction condition are not the simpler one or the regular one. They are somewhat different from your regular reaction, but still it is basic to your mechanism. It is a simple electrophilic aromatic substitution reaction. Okay, so again we take our benzene and we have formed our benzaldehyde. Clear? Now we will move to some reactions. So these are where all the reactions that were used to prepare our aldehyde. So we have prepared both this aliphatic aldehyde plus our aromatic aldehyde, that is benzaldehyde. Now we will move to the preparation of ketones. So we have many methods of preparation of ketones we have seen earlier, where we have used this, say, our secondary alcohol and treated with the stronger reducing agent or weaker reducing agent that would result in the formation of your, say, this ketone. Also we have seen that if we use this, say, ozonolysis, then we can also prepare the ketone and aldehyde depending upon the nature of substrate. Okay, now I would ask you a question here, that which kind of alkene would result in the formation of, say, your aldehyde or ketone upon ozonolysis. And I am saying that we will do a reductive workup. So how this ozonolysis look like? First of all, suppose we have this kind of thing. Suppose this is A, this is B, this is C, and this is D. Now I am saying that A is equals to B is equals to CH3. C is equals to CH3 and D is equals to H. This is the first question. Second, suppose you have A is equals to H, B is equals to CH3, C is also equals to CH3, and D is equals to H. This is the second. And the third one is A is equals to B is equals to C is equals to D is equals to CH3. This is the fourth one. Now what would you expect product from each of these? Try to solve it. Okay, try to solve it. So if you try to solve it, you will see that if A and B are both CH3, then upon hydrolysis this bond will break, and upon reductive workup it will result in this thing. That is ketone. Okay. Now if C, CH3 and D is H, then this side will result in, the right side will result in CH3H. Another illustration what it will give. So if you just try to solve it by yourself, I'm not doing this one. I'm giving the third one. Okay, so third one is both of these are CH3. All of the four are CH3, then it will result in 2 moles of CH3. Now what was the reagent that was being used? It was Me2S, which was giving the reductive workup, and O3, ozonide formation. Okay. Now this was the method. So I'm just giving you a question here to solve, because that would brush up your say concepts. So this was with the preparation of aldehyde. Now we move to preparation of ketone. Okay, we'll move to the preparation of ketone. So what we are using here? Okay, sorry. Yeah. So what we are using here? First we are using the acyl chloride. So this reaction happens in 2 steps. What are those 2 steps? So we treat, first of all, we treat our cadmium chloride and RMGX. Okay, we use our cadmium chloride and RMGX, and what it will result in? It will result in R2CD and MgXCl. MgXCl. Now what is happening here? Okay, what is happening here in this reaction? First step. So both of the R of Mg are being donated to your CD, and what are we getting? We are getting 2 Cl from this CD. So one CD will give 2 Cl, so both of the Cl are given here. So overall in this reaction, we are converting our, say, this Grignard reagent to this thing, and here RMGX is donating its alkyl group to this CD and releasing 1 Cl. Again the second mole of RMGX comes, and it is again donating its R to this CD, and we get R2CD plus MgXCl. Okay, so this is the first step. Now what happens in the second step? So we are here with our acyl chloride. So R2CD again react with this RCOCl to give this ketone plus cadmium chloride. Now in this step what happens? We have our CD and R. Now this is donated in this way, and it is kicked out to give our final product. Okay, so since CD has 2 R's, so it can say convert this 2 acyl chloride moles, 2 moles of acyl chloride to 2 moles of acetone, and we will get our CdCl2, not acetone, I would say, our ketone. Depending upon the substrate, it would be acetone or benzenone. That is a different thing. Okay, we'll get one ketone. What is the second method? The second method is called the treatment with Grignard reagent. So it is written very small, sorry for that. Let me give you the overall reaction here. We have this substrate, we have this reagent. Again this will act as a nucleophile, so this will attack here. This will move here. What it would result in? CH3, CH2, CH3 and double bond N MgBr. It would result in this kind of substrate. Now, I have told you multiple times that as we treat this imine with your water in present or acid, or if you do acid hydrolysis, this get quickly converted into your carbonyl group. So I would just make a point here. I would suggest you to remember this reaction, that whenever we treat our C double bond N with H3O plus, it get converted into CO. Okay, clear? So this was our mechanism of this reaction. So first we treated our C6H5 MgBr with your nitrile to give this adduct, and as we hydrolyze it, so imine is a very pro-reactive to this H3O plus, so it will be converted into carbonyl. So this was the preparation method for the preparation of ketone. Now you can think of one more reaction here. Okay, the Friedel-Crafts reaction. You can think of the Friedel-Crafts reaction. We can use the Friedel-Crafts reaction here also, as we have used in the Gutterman-Koch reaction, where we use CO, HCl, AlCl3, three of the reagent, one substrate, one your say catalyst, and one as your protonator, I would say. Here also we can use the Friedel-Crafts reaction for conversion of this say our benzene to this ketone. So you can think of it. It is not very difficult to think of. You can do the simple Friedel-Crafts acylation. Just take this benzene, treat it with CH3COCl in the presence of AlCl3. So that would result in your Friedel-Crafts acylation. Okay, clear? Yes. So if you are curious about the mechanism, then it goes like this. So you have your AlCl3. Now this is a Lewis acid. It accepts your electron. So what happens? This bond pair moves here, and this electron pair along with chlorine attacks on this AlCl4. So what would it result in? So it would result in CH3 O triple bond AlCl4 minus. Okay, now this center has high nucleophilicity. Okay, this center has high nucleophilicity. So this benzene pi electron attack on this, and we quickly get this ketone. Okay, so this is the overall mechanism of this reaction. So I have not put up this reaction, sorry for that, but this reaction goes like this. Okay, so this was the preparatory method for your ketone. So what are the reactions that we have seen? So I've just tried to summarize it. So first we have seen the reaction of the aldehyde, in which we have used Rosenmund reaction. In the previous class we have seen this reaction also. So basically we use PDBaSO4, and in the presence of your say HCl, and it reacts with your acyl chloride to give your say this thing, that is aldehyde. Further, next is your ETARD reaction, in which you treat your chromium Cr2O3, that is chromyl chloride, okay, CrO2Cl2 with your benzene, or sorry, toluene, to give your chromium complex that is further hydrolyzed to this aldehyde. Okay, so this was the method that we use. Then again we use this diol H. Okay, so the previous one was called as ETARD reaction. We can also use diol H. So we studied about diol H, that how this diol H can act as a hydride donor. So it is kind of similar to your BH3, that is borohydride, okay, borane, I would say borane, not borohydride, borane, okay, so which accepts electron from electron rich species and further donates its hydride to reduce that species. Clear? Also we are saying Stephen reaction, so it was having a very complex mechanism. It was basically having RCN, that is nitrile, that was further donated with electron by SnCl2 twice, which results in the formation of a negative species which is being further protected by the H plus, and upon the further say donation of the electrons, it was forming this RC triple bond, RC double bond and H2. Okay, this was further being hydrolyzed to your ketone, okay, sorry, aldehyde. So, and one more thing, the takeaway message I would say that every time we treat our say C double bond N with this imine, I would say imine with H2 and H plus or acid hydrolysis, it quickly results in the formation of your carbonyl group. Okay, so further we have seen these two reactions which was used for the preparation of your ketone, and at last we have seen the Friedel-Crafts acylation. Okay, also we have seen on Guterman-Koch reaction, which looks very complicated in first sight, but it was simply a electrophilic aromatic substitution in which we use a benzene, treat it with your carbon monoxide in the presence of HCl and AlCl3. Basically HCl was there to protonate the aldehyde, and your say this AlCl3 was acting as a Lewis acid, which we often use in this Friedel-Crafts reactions, and CO was used as a reagent. So upon the reaction of Ca with AlCl3, its nucleophilicity is increased and the benzene pi electron are being donated and the keto aldehyde is formed, that is benzaldehyde has been formed. So these were all the reactions that we have used for the preparation of aldehyde and ketone. Tomorrow we will start with the reaction of say aldehyde and ketone. So as I have told you earlier that the nature of the carbonyl group or the nature of the carbonyl bond is basically the deciding factor behind the reactivity of aldehyde and ketone. Although we have seen the structure of this, but tomorrow we will just give a quick recap to that so that you can connect that why is this reactivity aldehyde is being so. I would also suggest that in each of the reaction I have tried to put up the structure of the compound, because structure of the compound is very peculiar for the reaction of that species. So as we are introducing different say reagents to that say substrate, its structure is the main deciding factor that how it will react with your reagent. Okay, clear? So this is the most important thing. So with this I would end my lecture. So in the next class we will see the reactivity of this say aldehyde and ketone. Thank you.